having studied what are finite series of sequences, we can see what is an infinite series in this session. So, welcome to the class on infinite series. The sum of an infinite number of terms of a sequence xn of real numbers is said to be an infinite series, and it is denoted by summation n equal to 1 to infinity xn or simply summation xn. So, in the previous class we had seen summation to n number of terms on a series is summation n or k equal to 1 to n xk, but here we will be representing it as summation n equal to 1 to infinity. That is the only difference between the notation of finite and infinite series, but we are adding up the terms of the sequence infinitely or indefinitely we are adding to get an infinite series. So, as we keep on adding the terms of a sequence, we can see that some sequences have the sum of the terms of the sequences or series being added to a finite quantity, but some other terms or some other sequences are there whose terms add up indefinitely and go to infinity or increases as we move on and on. So, how we can classify these series in terms of this summation as finite or summation as infinite? That is what we call by the term convergence and divergence of an infinite series. So, there is something called partial sums. We are well familiar with the convergence and divergence of sequences, and we will extend that to series using this term so called partial sums. So, we can see what is a partial sum of a given series. So, suppose we have a series of the form summation n equal to 1 to infinity of xn. The underlying terms of the sequence are x1, x2, etc. up to infinity, this goes on. So, the first and the corresponding series, we can expand this series as x1 plus x2 plus etc. plus somewhere here you will have your nth term and so on, it goes up to infinity. So, the sequence of partial sums is created as follows. The first term S1 is nothing but the first term x1 itself, but the second partial sum will be the sum of the first two terms of the series, that is x1 plus x2. We are adding the first and second term alone. The third partial sum is S3, which is x1 plus x2 plus x3. So, keeping on like this or going on like this, repeating this procedure, we will be getting some Sn as x1 plus x2 plus etc. last term will be xn. So, this series is now converted into first partial sum, second partial sum, third etc. up to nth and so on, so that each of these is a new term and this constitute a sequence called sequence of partial sums, which is denoted by sequence Sn. So, we are getting, instead of a series, now we have a sequence of terms of real numbers, which is denoted by the sequence of partial sums Sn. And as I told you, we are well familiar with what is the convergence of a sequence of real numbers, and if this sequence of partial sums converges to a finite quantity, the entire series converges to a finite quantity. And if this sequence of partial sums goes to infinity, or if it is a monotonic increasing sequence which is unbounded above, or if it is a monotonic decreasing sequence which is unbounded below and so on, we can say that the series is also not convergent, we will say the series diverges. So, that is how the sequence of partial sums helps in determining the convergence and divergence of an infinite series. So, that is how we do this. As an example, we can prove that the series 1 plus 1 upon 2 plus 1 upon 3 plus etc. diverges. So, this is a very important series which every one of you have to keep in mind, because this series at a glance gives you an impression that we are adding only a fractional term or fractional number to 1. So, how can fractional numbers added to 1 be so large that the sum of the terms of the series diverges, goes to infinity? So, that is a question which can come to your mind, but this is a series which diverges. So, we can see its proof, that is like this: 1 plus 1 by 2 plus 1 by 3 plus etc. nth term will be 1 by n plus so on. So, this is the series that we have. Now, the method of proof of this is proof of divergence of this series is very a peculiar one, it is a very interesting one. We can write this one as, I will not write this notation here now, we can write it later, but I will do some manipulation here. This 1 I am going to write it as 1 by 2 plus 1 by 2, or you can even leave that 1 as 1 itself, no problem. This 1 by 2 we can write as the 1 by 2 itself. The next term to 1 by 3 is 1 by 4, which you can write or replace these two terms using 1 by 4. Then the next collection of terms that we are going to take is 1 by 5, 1 by 6, 1 by 7, 1 by 8. So, the sum of these 4 terms we are going to replace by 1 by 8. So, I am going to write it as 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 and so on. So, this goes on. The next collection will be how many terms we will be having? This is 2, this has become 4, the next will be 8 and so on. We will be replacing 1 by 9 up to 1 by 16 we will be taking together. So, 8 terms we will be collecting together. So, likewise we will be having this as, so now what is the notation that we have to put here? If we replace this 1 by 3 with this number 1 by 4, 1 by 5, 1 by 6, 1 by 7 with the number 1 by 8. So, remember that 3 is less than 4 and so 1 by 3 will be greater than 1 by 4. So, this is obviously greater than 1 by 2 plus 1 by 2 plus 1 by 2. So, these 3 terms are actually the same as these, there is no difference. 1 by 3 is replaced by 1 by 4 means 1 by 3 is larger than 1 by 4 because 1 by 3 is less than 4. So, this implies that 1 by 3 is larger than 1 by 4. So, similarly 1 by 5, 1 by 6, 1 by 7 replaced by 1 by 8 gives to a smaller fraction here, smaller collection here. So, you have a notation greater than or equal to on this side. Now, collecting these two together, this adds to 1 by 2, these 4 together, that also adds to 1 by 2. So, that is the trick done in this proof. So, we can see that summation 1 by n is now greater than 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2, every term is replaced by 1 by 2. So, how many 1 by 2's will be there? Infinite number of 1 by 2's will be there. So, 2 1 by 2's add to get 1. So 4 1 by 2's add to get 2, and likewise infinite number of 1 by 2's adds to get infinity. So this goes to infinity. And obviously this series, which is much larger than a series which goes to infinity, also goes to infinity. And this is the reason why we say that this series diverges. Okay. Now the next example that we have is summation r power n converges if modulus of r is less than 1. So this summation r power n is a geometric series which we had discussed in the previous class. So we can see its convergence using the sequence of partial sums. So summation r power n is nothing but 1 plus r square plus etc. up to infinity. Even if you start with n equal to 0 or n equal to 1, that does not matter, because if we add one drop to an infinite ocean, infinite number of drops of water, it is not going to change. So this is an infinite series, so addition of one term or deletion of one term won't affect the series, won't affect the convergence or divergence of the series. So if you take the partial sum Sn, that is the sum to n terms, this becomes 1 plus r square plus etc. up to r power n minus 1, and that is equal to, as we have seen, 1 minus r raised to n by 1 minus r if r is less than 1. Therefore, as n tends to infinity, so r less than 1 means r is the common ratio which is less than 1. So if modulus of r is less than 1, we can take r to be positive, that is why we are restricting to modulus sign. So any number, any positive number which is less than 1 is a fraction, and so if we have a fraction, the denominator term raised to n, r power n goes to 0 as n tends to infinity. So this term 1 minus r power n by 1 minus r, where r power n goes to 0 as n tends to infinity, forces this Sn to limit n tends to infinity of Sn as 1 upon 1 minus r, and r is a number which is less than 1, and so 1 by 1 minus r will be a finite quantity, and hence limit n tends to infinity Sn is finite means the sequence Sn converges, and so the infinite series also converges, as was required in the example. This was exactly what is given to prove in the example. Now the next question is also a series. Show that the summation of the series, or show that the series sigma k equal to 1 to infinity 1 upon k into k plus 1 is equal to 1. So this also we have seen in the previous class, it is a telescopic series, and so when you take the summation of n terms, Sn equal to summation k equal to 1 to n 1 upon k into k plus 1, we have seen that this is equal to 1 minus 1 by n. Therefore, as n tends to infinity, what happens to this expression? 1 by n, as n tends to infinity, goes to 0. So this becomes 1 minus 0, which is equal to 1, which is exactly what is required in the proof of that question. So we have summation k equal to 1 to infinity 1 upon k into k plus 1 is equal to 1. And if an infinite series converges, the limit is also called the sum of the series. Then only we will be able to write summation of 1 upon k into k plus 1 is equal to that limit. Otherwise, we cannot equate a series to a number if the series is not converging to that particular number. So this also can be read as sum of the terms 1 upon k into k plus 1 indefinitely is exactly equal to 1. So, that is another method of another way of reading this. Now, this is an important test for testing the convergence. If you are randomly given a series and you are asked to find whether it is convergent or divergent, you may not be in a position to find out all the partial sums and look at the summation of the partial sums, whether it is going to a finite number or whether it is going to an infinite number, like that. So, there are some tests which are available for us to easily look into an infinite series and test the convergence of the series. So, the first and foremost test which we have to keep in mind is what is called the nth term test, which says that if the series sigma xn converges, then the nth term goes to 0 as n tends to infinity. That is, limit n tends to infinity of xn is nothing but 0. So, the nth term is going to 0. So, how this is? We can see the proof of nth term test. So, we have seen that a series converges if and only if the sequence of partial sums converges. So, sigma xn converges if and only if sequence Sn of partial sums converges. Sequence Sn of partial sums converges. So, Sn, if you write, Sn was nothing but x1 plus x2 plus etc. up to xn, which is nothing but x1 plus x2 plus etc. plus xn minus 1 plus xn. So, we can even write the same expression like this. So, look at the first n minus 1 terms. This much constitutes our Sn minus 1 plus the last term xn. So, we have already established or we have already understood the fact that sigma xn converges if and only if the sequence of partial sums Sn converges. So, sequence of partial sums Sn converges means Sn converges means limit n tends to infinity of Sn is nothing but a finite number s. We can denote it as a finite value s. S is just a notation, a finite value. So, limit n tends to infinity Sn equal to s means what is limit n tends to infinity of Sn minus 1? When n goes to infinity, n minus 1 also goes to infinity. So, what is limit n tends to infinity of Sn minus 1? That is also equal to s. And therefore, we have written an expression Sn is nothing but Sn minus 1 plus xn. Therefore, xn is equal to Sn minus Sn minus 1, and limit n tends to infinity, xn will be nothing but limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1, and both these being s, the difference will become 0 as is required in the theorem. So, this is the proof of showing that if sigma xn converges or if an infinite series converges, then the nth term goes to 0 as n tends to infinity. So, this is what is called the nth term test. Okay. The next is another important criterion for infinite series, which is called Cauchy criterion for series. So, that is also can be treated as a convergence criterion or convergence test, we can say. The series summation xn converges if and only if for every epsilon greater than 0, there exists a natural number capital K such that whenever n and m are greater than or equal to k, where m is assumed to be greater than n, greater than k, modulus of n plus 1 up to n terms of the up to m terms of the series is less than epsilon. Now, the proof also follows from the concept that a series converges if and only if the sequence of partial sums converges. So, we have the proof given summation xn converges. So, this if and only if the sequence Sn of partial sums converges. And where does the sequence Sn belong to? The sequence Sn is a sequence of real numbers. So, sequence of real numbers converges if and only if it is Cauchy. We have established that result in sequences in Cauchy criterion. So, that is if and only if sequence Sn is Cauchy. Now, what is the relevance of Cauchy sequence, or what is the definition of Cauchy sequence? So, given epsilon greater than 0, there exists a natural number k such that for every m greater than n greater than or equal to k, modulus of Sn Sm minus Sn is less than epsilon, because the sequence Sn is Cauchy now. So, what is this Sm? Sm is the sum to m terms of the series. So, that is x1 plus x2 plus etc. up to xm, and Sn is nothing but x1 plus x2 plus etc. up to xn. So, the difference will be, because it is given m is greater than n, say m is like a 50 and n is like a 25 or n is like some 30 or whatever. So, the difference between these two will add up all the terms starting from xn plus 1 up to xm, and so this is equivalent to writing modulus of xn plus 1 up to xn is less than epsilon, which is exactly what is required in the Cauchy criterion for series. So, these two are the first and foremost theorems that we have to learn about infinite series and the test for convergence. There are many other tests available for convergence of series, which we will be discussing in the next class. Thank you.